Chapter 6.5 transitions from talking about simply warming up one object or letting an object cool off or mixing two objects that are different temperatures together to talking about if you measure the energy that comes from a reaction, how can you figure out like the rate that a certain reactant produces heat. So we still use calorimeters for those. This is a really similar to what we use, except this is a professional one. So inside what we call the chamber here, okay, that's where the reaction happens. If it's exothermic, then it's going to get really hot in there, and the heat is going to go into the surroundings. But one thing that you noticed from your lab is that we are making an assumption that water is the only thing absorbing energy, but that's not true. Okay, energy is really absorbed into the entire calorimeter, which includes the water, but also includes the walls of the container, the thermometer. If you have a stir rod in there, it has those. If you have the electrical charges in order to get a reaction to start, it includes that. So you have to make an adjustment for understanding how your calorimeter works. And you can't just assume that whatever the water says is 100% the energy coming from the reaction. And there is a standard for that. So somebody somewhere is in charge of figuring out what's the heat capacity of the calorimeter. So no matter what reaction is happening, the calorimeter is going to be absorbing a certain amount of joules every time water changes the temperature or the substance is releasing a certain amount of temperature or whatever. The energy that's absorbed by the whole calorimeter, which we have been calling Q of water, okay, Q of calorimeter is more than Q of water. It's going to be the Q of the water, the Q of the walls of the chamber, the Q of the thermometer, the Q of everything that could possibly be absorbing energy from the reactants. So if you know the rate and change in temperature and the standard heat capacity of your calorimeter, those two things together are the real Q value for the surroundings of your system. So here's our surroundings, which is the calorimeter, okay, and that Q is going to be the opposite of the reaction. The change in energy for a reaction is going to be measured in kilojoules per mole. So what we can get out of this equation is the kilojoules. Okay, we have to have other information to get the moles. So you're going to have at least a gram value of your substance to be able to figure out, on average, okay, what is the change in energy for every mole of a certain reactant. Okay, so page 264. So let's say we have a 1.10 sample of sucrose that combusts in a bomb calorimeter. Okay, it has a heat capacity of 4.9. You have a change in temperature. So we need to figure out what is the real Q. Okay, what is the actual amount of energy absorbed by the calorimeter? The standard heat capacity for the calorimeter is 4.9, and the change in temperature is 3.41. So that means our calorimeter during this reaction absorbs 16.7 kilojoules of energy. Okay, and it's kilojoules because the unit is kilojoules for the heat capacity. So, if we are looking for a change in energy, we now have the energy. Okay, but the change in energy is, the delta E is kilojoules per mole. So we have to figure out how many moles of sucrose were combusted. So we need to do moles of sucrose and do 16.7 divided by that. Sucrose is C12H22O11. So we have our 16.7 kilojoules. If we figure out moles, we need to do 1.010 grams divided by 342, and that is a very small number of moles. 0.00295. So the change in energy for sucrose combusting is 5661.0 kilojoules per mole. Okay, there were 3 sig figs in the problem, so I'm just going to round this to 5660 kilojoules per mole. So every mole of sucrose that combusts is going to release 5,660 kilojoules. You could also be asked to do these questions backwards. So this one is giving you the standard change in energy for toluene. Okay, and then it tells you when 1.55 grams of it are combusted in a particular bomb calorimeter, can you find the heat capacity of the bomb calorimeter? So we are going to eventually be using this. Okay, we're looking for this information. The first thing that we need to start with is Q-cal. Okay, so we have the rate of energy released per mole, but we need to know specifically for this reaction how many moles were there, and therefore how much energy was there, which is what the Q is. So the first thing we need to do is figure out how many moles of toluene we have. So toluene is C7H8. So we've got 1 mole is 92.15 grams. 0.0168 moles. Okay, so we know how many moles of toluene were combusted. We know the rate of kilojoules per mole. So if we take our molar value, moles, okay, multiply by negative 3.91 times 10 to the third kilojoules for every mole. Okay, now this is going to be solving for Q-cal. So we're getting rid of moles, and we're going to be answering just for the pure value of kilojoules created by this particular reaction, which is going to be the Q-cal. And that is 65.8 kilojoules. Okay, now one thing that's important to remember, okay, is that we have now transitioned into talking about the calorimeter, which means the amount of energy is changing direction. So this is now a positive 65.8 kilojoules, because instead of saying that it was lost by the toluene, we're saying it was gained by the calorimeter. So we don't know what the heat capacity of the calorimeter is, but we do know the change in temperature, which is 14.45. So now to solve for the heat capacity of the calorimeter, we just simply need to divide 65.8 divided by 14.45 is 4.55, and the unit is kilojoules per degree Celsius.